Hey there! Ever wonder how scientists can possibly measure something they can't even see? Well, today we're diving into a classic chemistry experiment to do exactly that. We're on a mission to figure out just how much space one single mole of a gas takes up. Let's jump right in.
It's a really interesting problem, right? We know a mole is just a way of counting particles. A huge number of them, sure, but still just a count. You can weigh out a mole of salt, no problem. But how in the world do you measure a mole of something like hydrogen gas? It's invisible, and that is the exact puzzle we're going to solve today.
So we're going to treat this like a scientific quest. Our goal? To find a very specific number called the molar volume of a gas. And this isn't just some random number for a textbook. It's a fundamental constant that's super important for understanding how gases work, in everything from weather patterns to industrial chemistry.
So here's our game plan. We're going to use the good old ideal gas law as our guide. We'll collect our data in the lab and then use that data to figure out the molar volume at something called STP, that's standard temperature and pressure. You can think of STP as the universal gold standard, a set of conditions that lets scientists all over the world compare their results fairly. Okay, first things first. We can't measure a gas if we don't have one. So this first part of our quest is all about the how. How do we actually make the hydrogen gas we need? And, just as important, how do we catch it once we make it?
The way we do it is actually pretty straightforward. We're going to take a small piece of magnesium metal and drop it into some hydrochloric acid. It fizzes up, the metal dissolves, and it releases all these bubbles of pure hydrogen gas. This chemical equation you see here, that's just the chemist's shorthand for what's happening. And you can see our prize right there at the end, H2G, hydrogen gas.
Now for the really clever part, how do you catch an invisible gas? We use this awesome technique called water displacement. You fill a tube with water, flip it upside down in a bigger container of water, and then you let the bubbles from your reaction float up into the tube. The gas gets trapped, pushing the water level down. And the space it creates, that's the volume of our gas. It's a simple but seriously brilliant method.
All right, we've captured our gas. Now it's data time. And I gotta tell you, the success of our entire mission really hinges on how carefully we take these next few measurements. Precision is everything here. So, we need to record 4 key pieces of information. First, the mass of the magnesium we started with. That tells us how much gas we should be making. Then, of course, the volume of the gas we collected. Next, the temperature of the water, because temperature affects gases in a big way. And finally, the barometric pressure in the room, which we'll need for our calculations.
Okay, we've got our raw numbers, but here's the thing. Those numbers only describe the gas under the conditions in our lab on this one particular day. Our quest is to find the volume at those universal standard conditions. To get there, we have to run our data through 4 essential calculations.
Think of this as our 4-step mission to get from our messy lab data to our clean final answer. Step 1, we'll correct the pressure. Step 2, we'll calculate the moles of gas. Step 3, convert the whole thing to STP. And finally, step 4, get that molar volume. Let's get to it.
And right away we hit our first little snag. Because we collected the gas over water, some of that water evaporated. So the gas in our tube isn't pure hydrogen, it's kind of damp. It's a mix of hydrogen and water vapor. Our first job is to figure out the pressure of just the dry hydrogen gas.
Luckily, the fix is super easy. To find the pressure of our dry gas, we just take the total pressure we measured in the room, the barometric pressure, and we subtract the pressure that's being caused by that pesky water vapor. But that leads to a new question. How do we know the water vapor pressure?
Well, this is the cool part. Water vapor pressure depends only on temperature, and scientists have already figured all these values out. So you just measure the temperature of your water, let's say it was 22 degrees Celsius, and you look it up on a chart like this one. At 22 degrees, the pressure is 19.8 millimeters Hg. You subtract that from your total pressure, and just like that, step 1 is done.
On to step 2, figuring out exactly how many moles of hydrogen gas we actually created. The great thing about this specific reaction is it's a perfect 1-to-1 deal. For every 1 mole of magnesium atoms we put in, we get out 1 mole of hydrogen gas molecules. So all we have to do is take the mass of our magnesium and divide it by its molar mass, 24.31, to find out how many moles we made. Simple as that.
Now for the big translation step. On the left, we have our lab conditions, our pressure, our volume, our temperature. On the right, we have the standard conditions, STP.
We need to figure out what our gas's volume, V2, would be if we moved it from our lab into that standard world. To do that, we use a powerful tool called the combined gas law. It lets us predict exactly how the volume will change.
We've done all the heavy lifting. We have our new volume, the one corrected for STP, and we know exactly how many moles of gas that volume contains. We are right on the verge of finishing our quest. It's time for the final step.
And after all that work, it all comes down to this one beautifully simple calculation. To find the molar volume, the volume of just 1 mole, we take our calculated STP volume, V2, and we divide it by the number of moles N we found back in step 2.
And boom! After you run the numbers, you get a result. A typical experiment like this might give you a value right around 22.1 liters per mole. That is our answer. That's the volume that 1 mole of our gas takes up at STP, according to our experiment.
So, how did our quest turn out? Well, we compare our result, 22.1, to the officially accepted scientific value, which is 22.4 liters per mole. Hey, that's not bad. That is really, really close. In a real lab report, you'd calculate something called percent error to see exactly how close you got. But this shows that even with some pretty simple equipment, we can get incredibly close to a fundamental constant of nature.
And let's finish with this final thought, because no experiment is ever perfect. What if you had a tiny air bubble trapped in your collection tube right from the start? That extra air would add to the volume of hydrogen you collected, making your measured volume bigger than it should be. Now, how would that one small mistake ripple through all 4 of your calculations and change your final answer? It's a great reminder that in science, thinking about what could go wrong is just as important as getting the right answer.